Oh, hello. I'm Richard Nafshin from Oregon State University, and this is a lecture hall here in Gilbert Hall where we do quite a bit of chemistry. It's a 4-story building, has a basement and goes up to 3, and really enjoyed this building. It's got some chalkboards, has some periodic tables. We do some demonstrations on the countertop and teach and learn some chemistry. The periodic table up here used to not have this red staircase. One night I came in with some red tape and separated these over on the left, which are the metals, from these over on the right, which are the non-metals. These right here on the border are often called semi-metals or metalloids because they can behave like metals or non-metals depending on what their environment is. The metals, they're not very fond of electrons and like to lose electrons. In particular, the group 1s like to lose 1 and become +1. The group 2s like to lose 2 electrons and become 2+. We will not talk too much about the charge that the transition metals, these 10 groups in the middle, like to take on. We can discuss if we're told what the charge is or what its environment is, but it's not fair to say these are 3+, these are 4+, these are 5+, 6+, 7+. They're transitional and they often change. Over here, these are the noble gases. The old term was inert gas, but we have since reacted some of them. Niels Bartlett at Cal first in the early 60s reacted xenon with some platinum and fluorine. But these don't take on a charge traditionally. They don't do a lot of chemistry, particularly for general chemistry students. So we say they're inert, relatively unreactive, and don't have a charge. These, over here, often called the halogens, will go ahead and gain 1 electron. The non-metals to the right of the staircase, but not including these gases, will go ahead and gain electrons. These will gain 1 and become -1. Gain 2 and become -2, gain 3 and become -3. We can talk about carbon actually gaining 4 electrons. There's precedent, there's example for this, and becoming -4. And boron is just small. People like to call it an exception, but it does its own chemistry. And so don't anticipate -1, -2, -3, -4, -5. Boron will quite often go -3. We do a little bit of boron chemistry. There's also one element I have to mention, that's sneaky aluminum. As I said before, these go +1, +2. Let's make a huge jump over the transition metals, and aluminum sneaks in at +3. When we're making ionic compounds, this gives us a chance to do the chemical combinations, such as calcium will lose 2 electrons and become calcium 2+. So when it bonds, forming an ionic compound with, say, fluoride, we cannot have the chemical formula of CaF. The charges don't wash. The charges don't cancel. 2+ -1 don't happen to wash out. So what we have to do is add another fluoride. And now our +2 charge is offset by minus and minus. Chemical formula is written as CaF2. We can do this exercise also with some polyatomic ions, such as sulfate. Sulfate has the formula SO4 2-. It behaves as though somebody was thinking about it being a non-metal with a negative charge. But we're not allowed to bust up the sulfur from the oxygens. The whole piece stays together. Chemical combination for, say, sodium sulfate would look something like this. A sulfate polyatomic ion has a -2 charge. When we combine this with sodium to make an ionic compound, sodium being in group number 1 would be +1, washing the charges. Not quite. We need another sodium. And now we get the cancellation of 2 positive charges with a 2 negative. Our chemical formula is Na2SO4.